So again, thank you to Gibran Rashid for inviting me and to the QWorld for organizing this course. I was told that we could talk about something interesting in quantum foundations and quantum theory. And I would be remiss if I didn't choose Bell's theorem, because it is near and dear to my heart. And I think it is sort of the best example of what makes quantum mechanics really exciting. And so it's a privilege that among all the courses that you have, I get to share Bell's theorem with you. So let me share screen and hopefully this works. Gibran, I guess you were saying that you want to collect questions. I'm perfectly happy to be more interactive. I can sort of keep a chat window open to respond on the fly.
Sure, that's fine.
What I was going to do is sort of go through a couple disparate PowerPoint presentations, pausing perhaps in between them, and then pulling up some Mathematica to do some actual demonstration of how to do the calculations algorithmically. So let's get into it. What I want to do is I want to imagine a thought experiment at the moment at a pretty abstract level. So I want to imagine that there are two people who are measuring something. Now, there are many ways that we could imagine a measurement. I could say, how are you doing? And I could be measuring your mood. I could open the door and say, is it cold outside? That's a measurement of temperature. I could say, what's on TV? That's a measurement, right? So I want to take a very abstract notion of what it means to measure something. But I want to imagine that there are two people and they're going about doing measurements. And they're not in the same place, but they're both doing measurements and they're recording it. And I want to sort of simplify that whatever they're measuring, we're going to imagine that it just has two outcomes: good, bad, plus, minus, hot, cold. We don't want to have sort of a scale here. For this level of simplicity, I just want to consider two outcomes for the measurements. And I'd like it that the way that the measurement is done can be sort of toggled. So I might, if I want to ask how people are feeling, I might ask one friend how they're feeling, and that would be sort of a measurement to this friend, or I could ask a different friend how they're feeling, and that'd be a different measurement, right? I'd be sort of measuring the same quantity, but in a different way. I'd be measuring mood, but on different people. Or I could ask, what's on television, but I could check one channel or check a different channel, back when people used channels to watch television, and that would be an outcome here. So just as an example of what we may be measurements, we could be measuring temperature. We could be not just asking what's on TV, but if we wanted to make it binary, we could take a screen of, let's say, a black and white screen, which is having a snow image, and just pick some pixel, like the top left corner, and ask, is this pixel black or is this pixel white? That's a binary measurement. We could flip a coin. That's a great example of a binary measurement. Charlie flips a coin, Alice and Bob look at the coin and they say, okay, is it heads or is it tails? That's the measurement. And what I would like to establish, and I don't think this is terribly controversial, which is that if two people are performing measurements, if Alice does lots and lots of measurements, and so she has this record of, on Monday I measured this, on Tuesday I measured this, on Thursday I measured this. If Alice and Bob do many, many measurements, and what they find is that whenever Alice does a measurement, Bob does a measurement, they get the same outcome, but that outcome is inconsistent. So it is random, right? Like sometimes you get heads, sometimes you get tails if you're measuring a coin, or sometimes it's hot outside and sometimes it's cold outside. But imagine that then they always get the same outcome. That kind of implies that they're measuring the same underlying phenomenon, right? If we're looking at coin flips, and I say, hey, I looked at a coin and it reports heads, and you looked at a coin and it reports heads. If we do this 50, 60 times, and every time I report heads, you report heads, and every time I report tails, you report tails, we're probably looking at the same coin, right? And if two people are reporting it's really hot outside and it's really cold outside, and they always agree every day, but whether it's hot or cold outside, then maybe they're living in the same area, same city, same region. This might not be controversial, but I do want to sort of emphasize that if we see the same outcomes of random measurements, it probably implies that there's some underlying common explanation there. And we'll formalize all this as we proceed. now let's go into like the quantum example of these kind of measurements. So I want to imagine that we're measuring photons, and the measurement is, does the photon go through a polarizing filter? So a polarizing filter is not very different from polarizing sunglasses. They're slits in plastic or in glass, and they can be very thin and spaced together. And for most light, about half the light will get through a polarizing filter. But if the light is already polarized, that changes things, right? So, I mean, the reason that polarized sunglasses are useful is that they're especially good at blocking out reflective glare from surfaces, from car glass or from lakes, and so they can be useful for seeing underwater on a shiny day, or for avoiding glare if you're driving. So we have these two photons, and they're coming down fiber optic cables, so we can put the photons wherever we want. It's just a light signal. And we're going to stick these polarizing filters in front of the fiber optic cable, and we'll put a camera behind the filter. And so then the measurement is, did the photon go through the filter, which is to say, was it sensed by the camera? Did the camera see light? Or was the camera dark that with the, tells us the photon didn't make it, it got blocked by the photon. And it got blocked by the filter. And we can rotate these polarizing filters, put them either like on a horizontal vertical basis or on a diagonal basis. And that would be sort of the different measurements that each person can do. So this is sort of a picture here. We're going to send light initially one sort of very high energy photon into a crystal, and it's going to become two low energy photons. So we'll have conservation energy. We can pipe the two low energy photons out on fiber optic cables, and then we just have these polarizing filters, which can be oriented differently. And there's detectors behind the filters, and we ask whether the photons go through. And the reason we say we have an Alice and Bob, Alice and Bob's A and B, so first letters of the alphabet. Alice gets her measurement. Does her photon go through her polarizing filter? And does Bob's photon go through Bob's polarizing filter? Alice doesn't know the outcome of Bob's measurement. Bob doesn't know the outcome of Alice's measurement initially. And Alice can choose how she wants to place her polarizing filter. Bob can choose how he wants to do his. And that's pretty much the end of the story, right? So why is any of this interesting? Because we get something which is really close to impossible. And I want to imagine what if we did this experiment and this is what we found. So imagine that we have configuration number one, which is to say the polarizing filters are both vertical. And so there's configure number one for Alice, but also configuration number one for Bob, right? And then we'll consider configuration number two for Alice and configuration number two for Bob, and we'll consider like mixing and matching. So maybe Alice is measuring in configuration one, Bob is measuring in configuration two. But let's start by seeing what we can infer from some knowledge about the experimental statistics. Suppose that when Alice and Bob are both using configuration number one on their measurement devices, so their polarizing filters are in whatever orientation which we call number one, that they always get the same result, right? So that if it goes through on Alice's side, if she gets a click in her detector, then the photon also passes through the filter on Bob's side, always. And if it doesn't go through on Alice's side, then it doesn't go through on Bob's side, and vice versa. So what does this tell us? It tells us that that the photon that Alice is measuring and the photon that Bob is measuring, they probably have some common origin, because they appear to share this property of, do they go through the polarizing filter? It is a property which is hard-coded into both of the photons, and they share it. So if we just took random photons from random light sources, we would typically not expect to see this. We would expect that there's a random transfer going through an Alice's side and a random transfer going through on Bob's side. But why should they be the same? And so if we get the same result for Alice and the same result for Bob, it must be that there is some property of the photon, and whatever it is, this property is, do we pass through the polarizing filter in configuration number one? That is, whatever it is written for Alice, the same as written for Bob, right? Let's add some more information. Suppose that now Bob switches to measure in configuration number two, because Bob has two different settings that he can perform measurements in. What would we infer if we see the same pattern, that regardless of Bob using configuration number 1 or Bob using configuration number 2, so long as Alice is using configuration number 1, Alice and Bob always get the same result. Meaning it goes through on Alice's side, if it goes through on Bob's side, if it doesn't, it doesn't. So then we would say, okay, what's our state of knowledge now? Our state of knowledge is, it does not matter whether Bob measures number 1 or number 2, at least as far as this property of does the polarizing, does the photon go through the filter, right? It seems like it doesn't make a difference for number 1 and for number 2. If whatever happens on Alice's side, it always agrees with Bob, same for number 1 and for number 2, which is to say Alice, as soon as she knows that the photon went through on her side and she was using configuration number 1, she knows whether it would have gone through for Bob, regardless of whether Bob chooses to measure number 1 and number 2, it doesn't make a difference, right? So this is sort of like what we would say is a false distinction. The measurement doesn't really matter. For example, let's go back to this example of measuring people's mood. Are you in a good mood or a bad mood, right? So I might have 2 different friends, and I could ask on one setting, I could say, hey, first friend, what's your mood? And my second setting could be, second friend, what's your mood? If these 2 friends always report the same mood as Bob's friend, if I'm Alice and Bob has a friend and Bob is asking his friend the mood, then I would say, okay, clearly we have a social circle here where Bob's friends and my friends are hanging out and they all have the same mood, and it doesn't matter which one of my friends I ask their mood. All right, so let's throw in another complication here. Imagine that Alice and Bob continue to get the same result. If Alice now switches to her second measurement configuration, so in this quantum experiment, it's she's rotated her polarizing filter, for example, and Bob measures number 1, then they continue to get the same result. It doesn't make a difference if it goes through on Alice's side, then it goes through on Bob's side. So fine. By the way, this discussion that I'm having right now is not something that I'm saying is done in a quantum lab. I'm saying, imagine if this could be done. What kind of conclusions would we draw? So now, if I've told you this much information, that they always get the same result, and it doesn't matter if Bob uses number 1 and number 2, and it doesn't matter if Alice uses number 1 and number 2. So then, what I haven't told you here explicitly is what occurs if they both use their number 2 measurement configurations, right? Because in all these sort of 3 descriptions, it's the record of the statistics when at least one of the parties is in configuration number 1. But from these, you could say there's nothing else to learn, right? If it doesn't matter if Alice switches between configuration number 1 and configuration 2, and it doesn't matter if Bob switches between configuration number 1 and configuration number 2, then clearly if they both do configuration number 2, they should get the same results. So what would happen if I told you that there was an experiment where if both Alice and Bob measured in configuration number 2, then they always get opposite results. Whatever Alice gets, Bob gets the other. You should say, this is not possible. Or is it? So in a classroom setting, if this wasn't Zoom, I would pause now and ask for people to sort of try to come up with some explanation for if we did see these kind of statistics, what could a possible explanation be? And since we're not doing an interactive seminar, I'll give you one possible explanation, which is that if I wanted to write this like a software, right? So I wanted to like have an app where Alice and Bob are using their cell phones, and Alice can, on her phone, open up this app, and she can say, I want to get a result from measurement number 1 and a result from measurement number 2. And Bob also has this app on his cell phone, and he wants to get an outcome, some binary outcome, and he chooses to push, which measurement outcome he wants to see, number 1 and number 2, on any given day. No problem. As an internet developer, I can make this app work. All I need to do is say, okay, which person, Alice or Bob, pushed the button on their app first. So suppose that Alice pushes the button on her first, and she wants to measure number 1. Okay, great. So she measured number one. I can make up a random number, give it to Alice. And now whatever Bob chooses, I'll just give him the same as I just told Alice. I need a random number generator. And if Alice chooses number 2 and she clicked the button first, no problem, I'll make up a random number for Alice. And then when I hear from Bob what he wants to learn, does he want to know the answer to question number 1 or the answer to question number 2? Well, if he wants the answer to question number 1, then I'll give him the same answer I told Alice. And if he wants the answer to question number 2, then I'll give him the opposite of the answer that I told Alice. So I can certainly make these statistics occur if I was trying to sort of conscientiously engineer them. But in order to do that, what I would need is that essentially the result of what Bob measures, namely what answer I give to Bob, should depend in some degree on the choice of measurement that Alice performed, right? Because how I respond to Bob is differently if Alice measured number 1 or Alice measured number 2, if Bob then measures number 2. I kind of need to know what Alice chose to measure in order to give the appropriate response to Bob. And so in the language of physics, we would say, yeah, that's possible, but this would not be what we call local, because it means that the results at Bob's end of the experiment need to somehow depend on the measurement that Alice chooses to perform, and potentially vice versa, depending on which party measures first. And at least this naive description, which was piping photons down fiber optic cables, we don't really see an opportunity for like, why should Bob's outcome somehow depend on Alice's choice? So it is puzzling, and we might say, okay, all we need to do is say that the outcome on Bob's side somehow depends, there's some sort of ghostly influence from the choice of setting that Alice does, or vice versa. The problem is we have other ideas in physics that we hold dear to our hearts, which is the idea of special relativity, and that is nothing travels faster than the speed of light. So we can take this thought experiment and we can make it hack-proof by putting Alice and Bob really far apart, right? So we know that no signal travels faster than the speed of light. So now consider the following version of the experiment. We take Alice and Bob, we put them very far apart, and we do the exact same experiment. So here you might imagine, let's go back to the apps on a cell phone, right? So Alice has her app, she can push a button and get an outcome. Bob has an app, he can push an outcome, get an outcome. Suppose that we did this though with an astronaut. So Alice is using this app on Earth, and Bob is using this app on the moon, which has a 2-second delay, or on Mars, which has a 7-minute delay at some points, up to 21 minutes, I think. It's for this configuration. So if we have Alice on Earth and Bob on Mars, then it's not possible to just have a cloud provider make this work, because assuming that whenever Alice chooses what to measure, she gets her response to that measurement immediately. Like, there's no time delay. There's no sort of waiting for a server far away to find out what she wants, which could then maybe be aware of what Bob wants and give her an answer. If when Alice chooses to do a measurement, as soon as she makes the choice, hey, I want to measure this, she gets the outcome. Then this ability to sort of explain things by non-local influence doesn't work anymore. And in principle, we can imagine this kind of experiment, which would then be a problem. And at this point, I'll say that quantum physics allows us to do something which is pretty darn close to this. We can actually have an experiment which is very, very similar to the one that I'm describing. It's not exactly the experiment I'm describing, and we'll get into the subtleties very, very soon. But let's assume, for a good approximation, that this is what happened, that we can send these 2 photons, one to Alice, one to Bob. Alice has 2 configurations for her polarizing filter. Bob has 2 configurations for her polarizing filter. We see this pattern of correlation between Alice and Bob's outcomes in configurations number 1, number 1, number 1, number 2, number 2, number 1, but we get anti-correlation or opposite results in number 2 and number 2. So this kind of is puzzling. This is what we mean by Bell non-locality, because it was John Stuart Bell in 1964 who realized that this kind of experiment was almost possible in quantum physics and that this was a problem. It also means that we can't imagine any possible way of saying that there is a predetermined outcome for the measurements. Because if the photon which is going to Alice, right, if as soon as it starts in the beginning, it sort of says, okay, regardless of what Alice chooses to measure, the photon has a built-in property ahead of time. Will it go through configuration number 1? And will it or will it not go through configuration number 2 for Alice? Right? Just suppose that that existed as a physical property. If that was the case, right, that this photon absolutely would have gone through configuration number 2 for Alice, that's a problem, because then what should it have done for configuration number 2 for Bob? Should it also have gone through? Evidently not, because whenever a photon goes through for number 2 for Alice, then it can't go through number 2 for Bob. So we have to say that it would then not have gone through for number 2 for Bob. But if it doesn't go through number 2 for Bob, then it shouldn't go through number 1 for Alice. On the other hand, if it doesn't go through for number 1 for Alice, then it should not go through number 1 for Bob. On the other hand, if it should not go through number 1 for Bob, then it should not go through number 2 for Alice, because they're supposed to always be the same. And yet we began by saying it does go through number 2 for Alice, and we end up with sort of this logic of contradiction. So one of the nice things about this is if we can actually do these experiments, which we can do in quantum theory, it tells us that the universe is philosophically different than the way we originally anticipated. You might have thought that there's some sort of Newtonian perspective of a clockwork universe, where whenever we do a measurement, what a measurement is it just reveals some truth that we did not know about, but it's a pre-existing value that we were just ignorant of. This perspective doesn't work if we can do this kind of perspective. It changes the very notion of what we mean by a measurement. There can't be this property which is pre-encoded. Rather, the only possible way that you can ever pull this off, if you can pull this off, is if the measurement results are not definite, if they're purely statistical, which is to say, any given photon, no matter what level of detail you have perfect knowledge about it, you could never know more than there's a 50% chance of it going through the polarizing filter and a 50% chance of it not going through the polarizing filter. There is no preordained property. That's kind of one of the things that this kind of experiment can teach you, which gives us the notion of randomness, private randomness, in a way that's very different. So previously we thought, what does it mean for something to be random? It means that there's some sort of complex phenomena like the weather or what people are going to tweet on Twitter, which is really hard to predict. But hard to predict and unpredictable are philosophically different. And here we're saying that if we could do the kind of experiments that I'm describing, then that would tell us that nature has something which is completely unpredictable, even from sort of a godlike perspective. There is no property. Nobody could know the results of this measurement ahead of time. And that's extremely valuable in sort of information theory. And time permitting, maybe we can go off on a tangent and discuss quantum cryptography. All right, so let me just jump to an example of a calculation here. So here I'm now drawing a diagram and I'm playing it as a game. So we have A1 and A2, which are these dots, which I can color in black or white, so they're binary. And there's B1 and B2, which is what should the photon do if Bob measures number 1? What should the photon do if Bob measures number 2? And we're trying to say, is there any way that we can assign colors to these dots in such a way that Alice 1 and Bob 1 always agree, as indicated by the blue line, Alice 2 and Bob 1 always agree, as indicated by the line, and A2 and B2 always disagree, as indicated by the orange line. And the answer is no, we can't do this, right? There's no coloring of black and white dots, which can recover the sort of ideal statistics that we're talking about. But the reason I want to now talk about this game is because in quantum theory, we can't actually do this experiment. I said I was going to come back to that. So we can't actually get 100% probability that Alice and Bob get the same outcome if they measure in configuration number 1, both of them. And we can't have it so that they always get exactly the same outcome if Alice measures in configuration number 1 and Bob measures in configuration number 2. But we can get close to that. So in actual quantum theory, if we follow the experimental predictions, we get about 85% probability of correlation. So there's an 85% chance that Alice, if she measures number 1, and Bob, if he measures number 1, are going to get the same outcome. It's pretty close to 100%, but it's not exactly. It's 85%. And so there's an 85% chance that A1 and B2 are going to be agreeing. There's an 85% chance that B1 and A2 are agreeing, and an 85% chance that A2 and B2, if we do that measurement, that they would get different outcomes. So now it's no longer so clear whether this is as surprising, because we don't have sort of the same kind of transitive logic. But by playing this game, I'm going to show you that that is also problematic, even if it's not 100%. So imagine that we could have scores, right? So for any time we have a hidden variable theory, a local hidden variable theory, so we can sort of color in these dots, we're going to give you a score where you get to assign properties to the photons, what they should do for these various filters, and you get +1 on your score for every blue line where they agree, or you otherwise you lose a point, and you get +1 if you can get A2 and B2 to disagree, otherwise you lose a point. So what you might find is that if you explore the different ways of coloring in this graph, then the sum of these 4 individual gains, right? Like, do you get a point for having A1 and B1 be the same? Do you get a point for A1 and B2 being the same? So we can treat them as expectation values, right? So either they're +1 or they're -1. And in this game where we're sort of awarding it so that if these guys are the same, that's +1. If these guys are the same, that's +1. Otherwise, if these guys are anti-correlated, we'll say this is equal to -1 and you lose a point. So of all local assignments, the sum of these 4 terms is always upper bounded by 2. Yeah, Ali, go ahead. You got a question. Ali, you have a question? Feel free to interrupt at any time, but I'm going to go on. How do you calculate the percentage 85%? Great question. I kind of don't want to answer that. This basically would require introducing a lot of the quantum formalism for measurements in states. Maybe you've had that in this course, I'm not sure. But the way it's done is you can set up a entangled state of 2 qubits between Alice and Bob, and then Alice is now performing measurements on her qubit, and Bob is performing measurements on his qubits. And so you can represent those as projective operator valued measurements, POVMs. And the notion of a different setting is a different basis for doing a POVM. So you've got 2 different ways of decomposing the identity operator for Alice, 2 different ways of decomposing the identity operator for Bob. And if you sort of do an optimization over these statistics, you can recover the 85%. But it's kind of tricky. And I would say another question sort of to follow up on that is not only how do you calculate the 85%, but why 85%, right? It ends up being like that we're actually measuring something related to like 2 plus the square root of 2 divided by 4. And why should that be the upper limit of nature, right? Like either we have to respect locality and nature is governed by hidden variable models, or it's not. right? That seems to be sort of the two attitudes. Like if we're going to sort of throw out all of our philosophical preconceptions, then why should the universe actually limit us to only being able to approximately pull off these statistics? Which is a question which I don't have the answer to, but many of you have thought about, and certainly something we could talk about further. The relationship between sort of Bell's theorem and Seroson's theorem, and they're not really terribly different. Well, so the idea here is that what Bell did is Bell showed that there are statistics which are impossible. That if you have a local hidden variable model theory, then there are constraints which really should be satisfied, and quantum theory doesn't have to satisfy them. Soros in the 1980s was the one who sort of studied the upper limits to what quantum mechanics could do. So it's actually very appropriate that you ask this question at this point, because if you want to know sort of like where the 85% comes from, it really comes from Soros's work in the 1980s. And this is exactly what I'm trying to say. So what Soros showed is that these kind of statistics are not possible in quantum theory, but these are possible in quantum theory. And what Bell showed is that neither of these statistics, regardless of whether they're possible in quantum theory, are compatible with predetermined local hidden variable models. And a hidden variable model is just the idea of a pre-existing attributes to values before they're measured. Putting them together, we say that quantum mechanics is really weird and requires us to throw out our preconceived expectations. So I'm going to switch now to sort of part two as we get a little bit more complicated and a little bit more formal. But if anybody has a question, I'd be happy if you unmute or put it in the chat at this time. No? Okay, then let's proceed. I'll share screen. All right. So now we're going to take a causal modeling perspective. So what does it actually mean to have a hidden variable model? And how do we sort of formally understand what its limits are? So here we're going to talk about the study of causality. And our main object is going to be these directed acyclic graphs, which I'm going to refer to as DAGs, based on DAG here. The idea is every circle, every node in a DAG is a variable, which is something that we might measure, or maybe something that we can't measure. So it's either an observable variable or a hidden variable. I'm going to draw the hidden variables with these sort of double boundaries to sort of indicate that they're not accessible. And then the arrows, which point into a node, are all of the things which are its causal parents, like what influences what. What can it depend on? So here, what you would naively think is that if Alice and Bob are measuring some common property, some attribute that has some causal explanation in the past, right? It could be that they're measuring a coin flip. So then the coin flip is lambda. If they're measuring the weather could be lambda. If they're measuring entangled photons, you might want to try to model the entangled photons as saying there's some dice roll which encodes the attributes of the photon. But we're all going to lump all that into lambda. And then this variable A is the outcome of Alice's measurements, and X is the setting or the configuration, right? Because what Alice ends up recording, like does the photon go through the filter or not, is an outcome. What could it depend on? Well, what are the ingredients which were relevant to that outcome? It depends potentially on what configuration. That's why we draw an arrow from X to A. And it could potentially on this common cause that was predetermined between Alice and Bob. So that's why we draw lambda. And so this is a DAG, which is an abstract representation of this sort of thought experiment that we analyze in a Bell scenario. And what I kind of want to convey here is a formal idea is that as soon as I draw down a hypothesis of such a causal structure, as soon as I say, I believe that these variables are described by some causal pattern like this directed acyclic graph, then that means there is going to be constraints on the observed statistics. And the constraints can take different forms. They might be inequality constraints, or they might be equality constraints. For example, we saw an inequality constraint in the first part, which was this game that you could play where this game has a maximum score of 2 over local hidden variable models. And so if you play this game with quantum theory and you get a score which is higher than 2, it tells you that you're not playing with local hidden variable models. But that distinction there, this upper bound on these functions of probabilities is an inequality. And so there's another way of writing that. And so this is another version of a Bell inequality, which is to say the probability of getting the outcome for Alice being minus on settings 1, 1 should not exceed the sum of these 3 probabilities, which is the probability of getting Alice getting a no outcome, Bob getting a yes outcome when Alice does configuration number 1 and Bob does configuration number 2. Right. So this is kind of how to read this probability term plus these other probabilities. An example of an equality constraint would be quite simply that X and Y here, the settings, they don't have anything in common. And so we should expect that there should not be any correlation between the choice of setting for Alice and the choice of setting for Bob, right? In fact, we expect that if you look at the joint distribution over their settings, it should factorize to some distribution, which is the frequency which Alice chooses configuration number 2, multiplied by the frequency which Bob chooses to do configuration number 2. Maybe they both choose to do it 50-50, maybe Alice is biased, but regardless, it should be a product distribution. And that is an equality, right? Like it says the joint distribution is equal to a product of 2 marginal distributions. So once we sort of formalize everything like this, where we have X and Y and A and B, X and Y are settings, A and B are outcomes, then we can start to write down data, right? And so this is actually the statistics that you get in a quantum experiment. So here, this is what we get if Alice is doing setting 1. And these are the 2 different outcomes for Alice. This is what happens if Alice gets number 2. So each of these blocks, each of these 4 sub-matrices here is one configuration pair, right? So this would be Alice doing 1 and Bob also doing 1. This is Alice doing 1, but Bob doing number 2. And each time we can fill in these 4 numbers, which are the probabilities of what's the probability that it goes through on Alice's side, that it goes through also on Bob's side or not. And so there's 4 possibilities in each configuration. It goes through on both sides, it goes through on one side, it goes through on the other side, or it doesn't go through on either side. And those 4 numbers have to sum up to 1 because probability is normalized. And so if you add up these 4 numbers in any block, you'll find they sum up to 1. And these are the statistics that you get. And you can see here that this is what we mean by an 85% probability of agreeing, because you can sum this where they agree plus this was with where they agree, right? So I'm kind of introducing a little bit more technical depth, but it's consistent with everything I've said beforehand. And if you look at this pattern here, when we look at setting 1 and for Alice and for Bob, we find that it's almost always the case that Alice gets the same result as Bob. If we look at number 1 and number 2, it's also almost the case, always the case that Alice is the same as Bob in terms of the outcomes A and B, similarly, and yet here you can see that the majority of the probability weight is in anti-correlation. It's on this sort of counter diagonal space. And so this would be an example of statistics which are incompatible with this assumption of causal structure. So if you thought this was your causal structure, and then you saw these statistics, then you could say, oh, I was wrong. That's not my causal structure. So what is the causal structure? That's an interesting question. So this brings us to like attitudes to how people interpret Bell's theorem. Let's see. Yes. So Elie, your relationship to cos squared theta is in fact 85% yes. I agree. So when we obtained these kind of statistics, what's the lesson? And this is where sort of philosophers start to disagree. Different physicists might give you different answers. Does it tell us that, in fact, our universe does have influence which goes faster than the speed of light, and that there is a problem with special relativity? I don't buy into that. But this is just sort of a way of using causal language to try to describe some things. So there's an attitude called superdeterminism, which is to say, oh, you thought Alice had free will in choosing configuration number 1 and configuration number 2? No. That's not true. Everything was preordained at the Big Bang. There is no such thing as free will. We're all just part of some giant universal wave function. And so there's no problem, because the sort of photons that Alice and Bob are measuring, they do have a causal past, but also the settings that Alice and Bob choose, they also have a causal past. Everything is confounded by sort of random variables that we're not aware of in their causal past. And if we take that attitude, it means that we're inserting these sort of extra arrows where we're saying that the settings are no longer independent. They can also depend on things that we cannot see. So this is one attitude. I don't like it. There's another attitude of retrocausality, which is to say, when Alice chooses what to measure, somehow then the moment the photon was generated and piped down the fiber optic cable, it's supposed to have this property of like, does it go through this polarizing filter or not? That property is written on the photon, which occurs earlier in time. But that property is written at time 0 by the choice of measurement that Alice wants to perform at a later time. So this is an attitude which has been posited by Fine and Wheeler and others. I still don't like it. But we could use causal language to describe that. And we could say whatever this sort of source of randomness which is being distributed in Alice and Bob, that is influenced directly by their settings. And that the settings play a role. And then there's this attitude, which is superluminal influence, which is to say, and this is kind of like how we would do things maybe in an app world, if we wanted to have like a decentralized server. This is maybe more of a centralized server, where we could just say, at Bob's side, the outcome depends explicitly on what's going on for Alice's setting. But if we posit that Alice's setting is something that she can freely choose, then how could Bob possibly be aware of that if he's very, very far away? And so that would mean that we have influences moving faster than the speed of light. So these are different attitudes, which some physicists would espouse is the moral of the story of Bellstein. The fact that we can, in fact, do these kind of experiments, the ones that I described the statistics for, means that one of these things is the correct explanation. I don't like it. So there is the attitude of spooky action at a distance, which somewhat works, because if you posit that there is superluminal influence, it's philosophically uncomfortable, but to be fair, mathematically, this causal structure, which is very different from this causal structure because it includes this extra arrow from X to B. If we put that arrow in, it changes the constraints on the possible data, and it allows for the observed data to be explained, right? This possibility of these 85, 85, 85, 15%, that is compatible with this causal structure. It is a valid explanation. It's just an awkward explanation. So this is why I have Canadian rap pop singer Drake saying, this definitely doesn't work. And this, it works. An attitude that I would espouse is that when we reject this, what we should do is we should be saying, okay, we're not need to like invoke influences faster than the speed of light. What we should really be saying is that we've just witnessed entanglement. We've witnessed the fact that we're not measuring something which is a hidden variable model. We're not measuring dice. We're measuring photons, and photons are not the same as coins. They are potentially a whole different species, and they obey different rules for calculating probabilities. And so instead of trying to pretend that there's some lambda and you're doing conditional probabilities involving lambda, say that there's some psi, and now you're doing traces on with POVMs on psi. So this is, I think, a much cleaner explanation, which is that we still are sort of making this adjustment, which we were saying it's not this causal structure, it's this causal structure, meaning it's not a hidden variable causal structure, it's a quantum common cause causal structure. So there is like a sense in which when we violate an inequality, it does help us reject one causal structure and move to a different explanation. Now, where I want to kind of go with this is beyond just this one causal structure. There's a lot of things that we can do here. But let me point out here that this is an abstract diagram of a causal hypothesis. There's many statistics I could observe for AB given XY if there's a hidden variable common cause between A and B. And there's a bunch of statistics that I could see if there's a quantum common cause between A and B. And it turns out that although they admit different compatible statistics, and therefore the constraints which one causal structure implies have to be different than the constraints another causal structure implies, I should point out that they only differ in terms of their inequality constraints. But every equality constraint, which is satisfied by this causal structure, is also satisfied by this causal structure, but they can have different inequalities. This is sort of like a major result in quantum foundations. So I did want to stress that. When we move to these non-classical common causes, the only thing that can change is the inequalities. And so here, for example, I say like, here's a sum of terms which is less than 0, and here's a sum of terms which is less than some other number, which is not 0, which provides more room. So now I want to talk about deriving Bell inequalities, because this is kind of where a computational attitude is useful. Getting a question in the chat. Which one is like your measurement somehow has an effect of a property that throws out at the start? So that would be what we call retrocausality. And that is this one here. So Bill Gonzalez, this is the one in which the settings influence the property at the start. Okay, so in order to describe the algorithm, I need to briefly introduce the idea of a polytope. A polytope is a way of describing a convex set. So imagine that you have a bunch of points in space, and I want to say, okay, these points, there's a region which is the region which is expressed as inside of those points. So there's two different ways I could describe this region. One is I could just tell you what are the points which describe the boundary of the region, which is called the vertex representation. And I could say, okay, here's a point, here's a point, here's a point, here's a point, here's a point. Everything that I want you to think about is inside the set is everything which can be expressed as living in the sort of convex hull of those points. The other description, which might be more convenient mathematically, is to say, okay, there's a wall, and you're going to be on this side of this wall. And here's another wall, and you're on this side of this wall. Here's another wall, and you're pointing here. And so if I wanted to describe a cube, for example, a cube is a region, it's a polytope. I could describe a cube by saying, okay, there are these 6 inequalities you need to know, like you're above the bottom, below the top, left of the right wall, right of the left wall, front of the back wall, in back of the front wall. Or I could tell you, like, these are the 8 points which define the vertices of the cube. They're equivalent ways of describing the same set of space, right? And I'm going to use the word polytope instead of polygon or polyhedron, even though a polygon and a polyhedron are perfectly good examples of polytopes, because a polygon is something which lives in 2 dimensions, right? You've got your octagons, hexagons, pentagons, triangles, squares. Those are all convex regions in 2 dimensions. Your icosahedron, dodecahedron, tetrahedron, cube, these are all regions in 3 dimensions. But we can work in higher dimensional vector spaces where you've got sort of 4 axes, 5 axes, and there's just your vectors have more and more dimensions in the coordinate system. But we can still describe things in either way. We can talk about inequalities. What do I mean by an extremal point? So a vertex, right? Like if you think about a cube, and I want to talk about the set of all points which are interior to a cube. Well, I can pick a point which is in the middle of the cube, but it's not an extreme point because it can be expressed as a mixture of other points. So an extreme point formally is any point which cannot be expressed as a positive linear combination of other points. I'm not sure if I have a good, well, yeah, so here, let's go with these. So these are examples of polytopes. So I have here like 103 and 202. These would be extreme points, but if I put a point here in the middle, then I could express it as like 50% this and 50% that. And so it's not extreme because it can be decomposed into more than one extreme component. Sometimes if a point is sort of on an edge, then it can be decomposed into at most 2. If it's on a face, maybe it can be decomposed into 3 or more. If it's in the interior, it can be decomposed as a convex combination of many of the extreme points. So why am I bringing up polytopes? Because there's software for taking a set of vertices and converting them to a description in terms of inequalities. Or if I have a set of inequalities which describes some region, I can find out what are the extreme vertices of that region. This is called a convex hull problem or a polytope representation conversion problem, which allows me to just do this kind of thing. And it's quite relevant because what's actually going on in when we try to discover Bell inequalities is that we're doing exactly this. Let me explain why. The idea of a hidden variable model is that we're trying to imagine what are the possible assignments to the outcomes ahead of time. And so there's different ways that we could assign outcomes of measurements. But there's only so many different ways that we could assign outcomes of measurements deterministically. Like this, if we go back to that graph where I had these like blue lines and dots, which I could color in as black or white, there's only so many ways that you can color in those dots. And so we call these local deterministic strategies. The way it works is that if you write this down on pen and paper, you can say, okay, let me go back quite a bit. So here I have, for example, 16 probabilities, right? Which describes my experimental statistics. So what I'm going to imagine is that I have this matrix of matrices. So it's these 16 probabilities. And these 16 probabilities, I can say, what do these 16 probabilities look like for every deterministic assignment of outcomes? And a deterministic assignment will say, okay, for each one of these sort of submatrix blocks, it's going to be a 0 everywhere and a 1 somewhere, which is what happens on Alice's side, what happens on Bob's side. So I'm going to go through this in great detail. So we're going to sort of spiral back to that. Once we are able to enumerate these strategies, which is, okay, this is what the probabilities would look like if it was this assignment. And this is what the probabilities would look like if it was this assignment. And they're not really probabilities, they're kind of assignments. So we end up with these things which look like 0 and 1 probabilities. So they're deterministic assignments. What the hidden variable allows us to do is it allows us to assign some sort of mixture to them. It could say, maybe it's a little bit of this, a little bit of that. And our ignorance, if they did have preordained values and we just did not know what they were, then we would say that there is some distribution over possible assignments ahead of time, which means that to be a distribution which is consistent with the hidden variable model, the set of probabilities that we would see should be one which could be expressed as a convex combination of deterministic assignments. That's the key idea. And so once we understand that, we could say, oh, it's very easy to enumerate the vertices of the space of distributions which are compatible with a given causal structure. We can get what the extreme probability of AB given XY look like. We just want to know what that set looks like. And then to discover the inequalities, we go to this sort of polytope representation conversion software where we go from the vertex representation to the inequality representation. And I'm going to do the calculation live in front of you at the end. Gibran, would you do me a favor and let me know when I have like 10 or 15 minutes left, because I really want to make sure we get into the calculation point.
Sure.
All right, so if we're considering 2 settings and 2 outcomes, then there are going to be 16 deterministic strategies, and they're going to end up giving us 8 Bell inequalities. So here is an abstract representation of that. So if it's a deterministic representation, they might look like this. So remember, we have these like 4 by 4. If these are the different probabilities here. So this is all on setting 1, 1. This is on configuration 1, 2, these 4. And this is the no, no, yes, no, yes, yes, no, yes over here. And so once we say, okay, in order to assign this, we need to know what would happen to Alice if she did X, what should happen to Bob if he does 1. So here, if we look at this example, this is one in which it looks like Alice, this is Alice doing measurement number 1, this is Alice doing measurement number 2. So you can see here that if Alice does measurement number 1, what does she get? She gets yes, +1, because it's always on this side and never on this side. And here, if she does the second one, if Alice measuring number 2, she gets a no. But if we look at it from Bob's perspective, here, if Bob is doing measurement number 1, then he gets a no. But if Bob is doing configuration number 2, he gets a yes. If we look at this as a different deterministic strategy, this would be a different vertex of the Bell polytope, then this is one in which Bob gets different answers. So here it's a no, here it's a yes. But for Alice, it's a yes and also a yes, regardless. And so there's different ways of filling these in. If you work it out, you'll find that there's 4 choices for assignments to Alice for both of her X values, 4 choices for what Bob could do for his Y values, because we have for Y equaling 1, what do we do for Bob? For Y equaling 2, what do we do for Bob? For X equaling 1, what do we do for Alice? For X equaling 2, what do we do for Alice? And those are 2 choices, 2 choices, 2 choices, 2 choices. That gives us 16 total vertices. And if we work this out, there are these sort of 16 rows now. And each row here, I've expressed in terms of the possible probabilities. Coincidentally, there are 16 probabilities. That's a coincidence. We could have more probabilities than there are possible assignments. We could have fewer, but in the particular study of the Bell scenario with 2 settings and 2 outcomes, it ends up being 16 probabilities and also 16 possible configurations. So that each row of this matrix is an assignment to probabilities. And so I can take this matrix and I can just dump it into the software and say, hey, every row here is a vertex. Tell me what the inequalities look like to describe the same region in space. And now you get this H rep, which is called the half space representation, as opposed to the V rep, which is the vertex representation. And we find these inequalities. Some of these inequalities are really interesting. Like this is a Bell inequality, which is the one that we can violate with quantum statistics. Some of them are kind of silly. Like if we ask, okay, if those are the vertices, then you'll note that this probability of this one term is never less than 0. That's not the kind of thing that can be violated by quantum mechanics, right? You can't have negative probabilities for the likelihood of a given event that you can actually observe. That doesn't happen. So these are kind of trivial inequalities. And sometimes we might also discover equality constraints. Because, for example, if I had, let's say, a cube, right? But I chop off the 1, 1, 1 corner, and I chop off the 0, 0, 0 corner of the unit cube. Then I still, instead of having 8 vertices, I now have 6 vertices. Those 6 vertices, although each vertex is expressed in terms of an X coordinate, a Y coordinate, and Z coordinate in 3 dimensions, they only span a 2-dimensional subspace, right? I don't know if you can imagine that. It's like a hexagon, which is the slice through the middle of the cube. And so you might end up with a description which says, okay, although you've given me these vertices in a 16-dimensional coordinate system, there are actually equalities, which means that the dimension of this polytope is in a lower region, because it's every equality is tells you that like you're both above this half space and below this half space, i.e. you're on this half space. And so this is what we call a no signaling equality. And it's worth pointing out here that what we're doing here is we're saying, if we sum over Bob's outcomes and we ignore, it doesn't matter whether we consider Bob getting outcome -1 or outcome +1. So it's the sum of these 2 terms This is Bob getting -1. This is the sum of Bob getting +1. So if we add these two together, which is to say we trace out Bob's outcome, then it should not matter if Bob switches settings, which is what is going on here. So these two probabilities is always equal to the sum of these two probabilities, because if we sum over Bob's outcome, it doesn't matter what setting Bob was using. We're just left with a marginal else, and it doesn't matter what's going on here. Okay, so I'm going to go ahead and skip that. And sort of give us a description now. So in the abstract, what we see is that there are these deterministic strategies, which tell us, like, if there was a hidden variable model, then we would expect the probabilities to be expressed as some convex combination of deterministic assignments. They form some region, which abstractly I'm going to say is this green box. The statistics that we can get in a quantum experiment, if we don't have a hidden variable model, but we have the same causal structure, except instead of hidden variable models, they're quantum common probabilities, then we get a bigger set of compatible statistics. And so I'm going to draw that as this orange circle. So the orange circle includes everything that you can do with the green square, but allows for more statistics. And this is a terrible picture because it's a two-dimensional graphic when we're talking about the set of statistics that you could get, and the set of statistics are quite large. They involve 16 coordinates, and even with equality constraints, there's still 8 dimensions to be visualized. But as humans, we can't see 8 dimensions, so it'll have to go. And this blue outer region is stronger than quantum. It's everything that you could possibly imagine, such as the thought experiment of the 100%, 100%, 100%, and 0% ideal experiment. It's not achievable in quantum theory, but it's still sort of philosophically consistent. And so we'll draw that with this blue region. I think I'm going to go ahead and skip the discussion of quantum cryptography at this point. So let me move on to a description of more general causal structures and more discussion of causal inference, and then we'll conclude with some actual coding. So let's see here. Yep. Oh, I gotta press the button. There we go. Good. All right. So, if we're now going to move beyond quantum foundations, we can say that there's a more general attitude where statisticians, data scientists, epidemiologists who don't care whatsoever about quantum common causes and quantum entanglement, they still care about being able to draw descriptions of causal hypotheses and falsify them and say, like, here's a hypothesis for my data. It could be data nothing having to do with the quantum experiment. And it's sometimes really useful to sort of understand whether your data fits a DAG. A DAG is a directly acyclic graph, which represents a causal hypothesis. And there's a task in this field of causal inference, which is called causal discovery, in which you observe some data over multiple random variables, and we try to figure out what is the description of the causal relationships between these random variables. And this basically means that we're going to just consider many, many different DAGs, and we're going to ask which ones are valid explanations, or which ones are the best explanations. This is sometimes done in artificial intelligence. If you're trying to have a machine come up with sort of a model to describe given statistics, there's a way of putting this into the back end. So let me describe a little bit about causal discovery. Suppose that we observe data about smoking, cancer. There's presumably a causal link between smoking and cancer. In fact, nowadays we believe smoking causes cancer. But suppose that you just observed a bunch of people and you say, hey, are you a smoker? Yes or no? Oh, do you have lung cancer? Yes or no? And you find that there's this correlation. In fact, S and C are going to be these variables. So we're going to see that there's correlation between whether you smoke or not and whether you got lung cancer or not. So you observe that correlation. And you also find that if you are, say, doing autopsies as a medical examiner, that there's a correlation between having tar in one's lungs, black lungs, if you're a smoker, and having cleaner lungs if you're not a smoker. It's not 100% because maybe you work in a particularly polluted environment, so you might have tar even if you're not a smoker, or maybe you smoked but not enough to develop tar in your lungs. I don't know. And we also see a correlation between lung cancer patients who have lung cancer and tar in their lungs. But suppose we see a conditional independence, which is to say that if we stratify the data according to whether or not somebody has tar in their lungs, then there's no longer any correlation between smoking and cancer, right? Which is to say, the population which have tar in their lungs, there's no correlation in that subpopulation between whether or not you have smoking and cancer, or the people who have no tar in their lungs, there's also no correlation in that subpopulation between having tar and having cancer. So this is what you see in the world. And then the goal is, does smoking cause cancer? And so what you can do is you can say, how many possible causal relationships are there between three random variables, S, T, and C? And there are many. And so here's a description of, what is this? This is some 25 different DAGs, right? But most of the DAGs fail to explain the data. And so we can sort of rule them out. Because here, for example, in this one, where we say that the tar is caused by smoking and it's also maybe depends on cancer, and cancer and smoking are the root variables, then we would not expect to see any correlation between smoking and cancer, even if we don't condition on tar. And so it fails. And then you're left with these, which are the ones on the outside. There's 9 remaining. And this is just sort of a shorthand description of causal discovery. Have data, what are the DAGs that fit the data? Of course, we could always say, maybe there's some unobserved common cause, a hidden variable, which just influences everything. So I can just take this causal hypothesis, which is there's something that I can't see. It's a wizard did it, and it made all the data the way that it is. It always works. It's always a possible explanation. But if you invoke that as a DAG, we don't like it because it's too powerful, and we want to find sort of the weakest causal explanations. And we codify this with this notion of faithfulness, which is to say, if there's a lack of correlation between two variables in my data. So if I'm looking at multivariate data over, hold on, I'm seeing in the chat. What are mu and lambda in that causal diagram? They would be hidden random variables. So they'd be unobserved hidden variables. Very nice. I should have clarified that, yes. Because we can consider causal diagrams which involve hidden variables or causal diagrams which do not involve hidden variables. But if we're considering all possible ways that some observed variables can be related, then we throw in hidden variables into the explanation as well. So we generally say that if two variables do not exhibit correlation, then the DAG should not be one in which they could be correlated. Right? Like that independence should be enforced by the causal structure, because why else would there be statistical independence if the causal structure doesn't demand that they be independent? So there's ways of sort of using this to reject overly powerful explanations. Now, if we try to do causal discovery, which is there's off-the-shelf algorithms for causal discovery, you put your statistics in, and causal discovery is done for you. And what you typically hope for, at least in the description of causal discovery that I'm describing, is that you get maybe one, maybe a few potential DAGs back, which are valid, faithful explanations. They're ones where there's all of the independencies, all the statistical independencies in my data are strictly implied by the DAG, and also the DAG is capable of explaining the data. If we put in quantum data, such as this, it turns out that if you run a causal discovery algorithm, it fails completely. There are no DAGs whatsoever which are faithful. The problem is, we said this is a valid causal explanation, which is the one that I didn't really like. It has this superluminal influence where the outcome on Bob's side is influenced by the segment analysis side. The problem with this is, from this perspective of causal discovery, Bob's outcome should be statistically independent of Alice's setting. This is something that we see in a quantum experiment, because Alice's setting does not, we believe, actually influence Bob's outcome. So if we don't see any correlation whatsoever between Bob's outcome and Alice's setting, then we say this is a bad explanation. And so when we run this, we end up with this failure, which is quite nice. So there's a nice paper, which is that, causal discovery fails on quantum DAGs, so that's worth mentioning. And if you're asking, like, is this really a thing? Yes. So I did sort of a sampling of papers across different fields. And this is just a way of saying these directed acyclic graphs, they show up regardless of what discipline you're talking about. So here it's some social, science, dental causal structure. Here's one on agriculture. Here's one on disease and various medical symptoms and causes and conditions. One of the tasks that makes the rest of the community, which is doing causal discovery and causal inference, pay attention to the work that quantum physicists are doing, is that when we have these hidden variables, it becomes quite difficult in practice to determine whether the data is compatible with a given DAG. So this idea of using polytopes to say, oh, well, we have a hidden variable and therefore we can do this vertex representation, and then we can use that to test whether or not the data fits the DAG, is really a very powerful insight. That's something that came from Bell's theorem and is totally relevant to data science beyond Bell's theorem, but is really only in the last decade being appreciated by statisticians in other fields. Because these kind of ideas of like positing hidden variables is quite common. Like it's very hard to actually do serious statistical work and say that you've controlled for absolutely every possible confoundment. Yes, it is like AI in the sense that you're coming up with decision trees. So the difference between causal discovery and AI is that AI is mostly about pattern finding and extrapolating forward, whereas causal discovery is coming up with a causal model such that not only can you predict what's going to happen next, but you can then have a sense of what, if you change something, how would that change the predictions going forward, even if it was beyond the training. So, okay. These are examples of causal structures, which I just haven't labeled, which have more than one latent variable. So this could be 3 observed variables, which have 3 different unobserved hidden variables connecting them. We call it a triangle scenario. And this is one which has some directed influences. So here, this is somewhat of a setting because it influences this, but it also is an outcome because it depends on some common cause. These are the kind of things where statisticians are getting stuck, and this is where sort of my own research is currently directed, right? What I think a lot about, which is how to understand the inequality constraints which are implied by DAGs which have more than one latent variable. But the nice thing about Bell's theorem is that it works if we want to understand the constraints that are implied by DAGs, anytime there's a single latent variable, even if it's not this one. So here I've discussed already like how to identify the Bell inequalities, which is to say, if this was your causal structure, how do you find the inequalities which are implied that you can then use to test and falsify whether or not that's a valid explanation for your data, assuming classicality. But what if you wanted to understand what are the limits of this DAG? What are the limits of this DAG? What are the limits of this DAG? The beautiful thing is it's exactly the same idea, which is that we can do the deterministic strategies. Except now, what we do is we'd say, okay, suppose that we have this last one here, which is this instrumental one, X points to A points to B. This actually shows up a lot, and I'm going to spend a great deal of time talking about it. But I just wanted to point out that before we do so, these kind of DAGs with one hidden variable, it's not really that much of a special case. There are many, many situations where we're doing causal discovery, and they're all relative to DAGs which have a single common cause. So this is in sort of hierarchies of non-locality. This comes from a sort of a game theory paper about multi-stage scheduling. Okay, so let me say a little bit more before I actually move on. The way we would discover the polytope is we would say here, let's say A and B and X are binary. So what we would do is we would say there's only so many ways that A could depend on X. So we say, okay, for every value of x, what could A be? And we make an assignment. We say, this is what A is for both of these values of x. And then we'd say, okay, for every possible value of A, this is what B would look like for any value of A. And so you decide those. You've got two choices. What is A for every value of x? What is B for every value of A? And then you can put it together and you say, okay, suppose that x is 0. What would you see? Well, then A should be something and B should also be something. Because you can just work through it, right? Because once you know what A is, then you know what B is. And that's for one strategy. And you can say, for if X is the other thing, what should A be and what should B be? And you get a assignment of the probability of A, B given X for both values of X and all values of A, B, which are pre-assigned for every hidden variable, for every deterministic strategy. And then everything else is a convex combination theorem. I'll do the calculations at the very end. So the other thing that you can do beyond causal discovery is causal inference. And this is something which is really a hot topic, because here what we're doing is we're not trying to understand what is the causal explanation, but where you believe you already know what the correct causal explanation is. And what you want to understand is, if you were to intervene and change something, can you predict what's going to happen? So here, for example, is a hidden variable DAG, which connects X and B. And also we have other arrows, so it's a random DAG. And we might say, okay, suppose that A and B are statistically correlated, right? If A goes up, B goes up. There are many explanations here for why A and B correlate. Is it that there's some functional dependence of B on A, that A is influencing B, so that if I change A, that's going to change the value of B? So check comment in the chat. This is interesting in some sense because we study DAGs to represent various algorithms problems. Oh, we're gonna have to talk about that because I don't know why you study DAGs to discuss algorithm problems. So let's do that at the end. There are other possible choices though, is that maybe A and B, maybe A doesn't influence B at all because there's this sort of backdoor path, right? There's this common hidden variable which goes through X. And so maybe if we were to change A, that would have no impact on B. And it's just the only reason we see that A and B are the same is because naively they are the same. So you can imagine like snipping A from any past dependencies in a counterfactual sense and say, suppose that that B did not actually have this value of A that we saw. What if B was exposed to a different value of A? What would happen? These are counterfactual questions, but we can answer these counterfactual questions using the same language. It's just a discussion of probabilities that we can't see. So here's a whole bunch of examples where we have this we call confounded correlation, where there's a direct effect and also a common cause effect. So we could say in medicine, does a treatment result in a better health outcome, right? If I take this drug, does it make people get better? So I find maybe that there's an exercise regimen and the people who do this exercise regimen are very healthy. Does that mean that doing the exercise regimen makes you healthy? Or is it the fact that healthy people were the ones who were able to do the exercise regimen, right? I'm reminded of sort of a silly story, which is people did a study. What is the a food which makes you healthiest? Like if you look at people's diet and you look at the healthiest people, is there something in common among very, very healthy people that they consume more of this food or beverage than the rest of the population, which is not this sort of special healthy subgroup? And a study was done and it found that yes, in fact, sports drinks, Gatorade, Powerade, are more consumed by healthy people than by non-healthy people. Does that mean that drinking Powerade makes you healthy? No, it means that the healthy people are exercising and that's why they're consuming these extra things. You might ask, if you smoke, does that increase your risk for COVID? Actual paper that I read about recently. It turns out that there was some really bad statistical analysis done because people found out that among people who were experiencing great difficulty breathing when they first entered the hospital, it was smokers who had better likelihoods of recovering from COVID than non-smokers. Yeah, it's not that smoking makes it likely for you to recover from COVID. It's that if you're a smoker, that kind of explains why you are having really bad difficulty breathing. And so you don't need to say that it's the same severity of COVID if you're having trouble breathing as a smoker, whereas if you're having trouble breathing as a non-smoker, that's an indication that your COVID is more severe. But these kind of causal analyses are all about picking apart causation and correlation. So this is sort of a scenario that I guess is the last one I'll do in the abstract. It is called the instrumental scenario, where we say that A could influence B, but A maybe is also just confounded with some common cause, a hidden variable with B. But we have access to another variable X, which influences A and is not confounded with the hidden variable lambda. And we want to know what's the direct effect of A on B. So where does this show up? It shows up everywhere. Here's an example. There's the medical example I gave you was if we see correlation between exercise and positive health, does that mean exercise makes positive health? Maybe. Is there anything else that we could do? Well, I could consider a third variable, X, which is an assignment to whether or not you should exercise. So maybe I just pick some workplace and I say, okay, we're going to mandate some exercise regimen in this workplace, but I don't do it at some other workplaces. It might not be, a totally randomized control trial, but the idea of like, are people healthy beforehand, that definitely doesn't determine their assignment. And maybe if I say, everybody here is rewarded extra money if they exercise, maybe not everybody there exercises, right? I'm not saying that you exercise if you're told to exercise, but we can consider it an assignment. Nevertheless, if you see a correlation between the assignments and the outcomes, so if you see that people who were told to exercise are generally healthier than people who are not told to exercise, maybe this tells you that, in fact, the exercising is what makes them healthy, right? And so this is kind of what we're going to use to determine this, but it shows up in other places. This is one of my favorite examples here, which is suppose that there's a sports movie and you want to put a lot of money into advertising a sports movie. So you spend a lot of money to advertise, people should go watch your sports movie before a big sporting event like the Super Bowl. And you find out, and you poll people, that the people who saw your ad were more likely to go to the movie. Does that mean that your ad made them go to the movie? No, not necessarily, maybe. But maybe the ad was just watched by more people who are sports enthusiasts because the ad was on a sports show. And then it's also the sports enthusiasts who are the ones who watch the movie, so they would have gone anyway, and your ad didn't influence them. But if you can say, let's say that there's this X, which is like the city where people live in, where the Super Bowl is. If you see that people in that city are going to watch your movie more than people who live in other cities, that would be actually more interesting because this tells you that maybe your ad was effective. And it's not just the passion for sports. It's this other thing, which is uncorrelated with one's passion for sports, because whatever city the Super Bowl is in is not a function of whether or not people in that city like sports, right? It could be in any city with a major team. And so we can use these kind of examples. And the way we actually handle this is that we say, okay, we observe data for X, A, and B, and maybe these other situations here. And we're imagining a counterfactual DAG, which is what if you could influence B by some choice which was not determined by the confounder. This is what you want to know. Like if you change A in a way that doesn't depend on the hidden variable lambda, what would happen? And so you can say, I'm going to set up the statistics on this DAG. And it's a single latent variable DAG. And so we can have the constraints, the inequality constraints for all the distributions which are compatible with this DAG. But of course, this is not the observed DAG. This is a counterfactual DAG with a hidden variable model. And you can say, I don't see the statistics on the counterfactual DAG. I don't have access to the W A, B, A sharp, Y, and X. Like that's not something I observe. Thank you very much. And yet you have partial statistics because you know that if A and A sharp coincide, then you know those probabilities. And so we end up being able to compute this. So I'm going to switch now to the last thing, which is just some live programming to sort of show you what it looks like. So here, let's go to this. Can everybody see the Mathematica screen, or is it too small? I'll increase the magnification a little bit. Let's see here. Like so. So if we wanted to sort of study the Bell scenario, which we're going to go back to, which are these sort of 4x4 grids, we could say these are local deterministic strategies, because they say, okay, this is for Alice, where does she do for setting 1? What does she do for setting number 2? And so we have a choice. Do we put a 1 to the left or to the right? And here, do we put a 1 to the left or to the right? And we could do the same here. And then it's these products which form the joint probability. So if you do this, these are the 16 deterministic strategies for the Bell scenario. And of course, these are the symbolic probabilities for the Bell scenario, just to review. And I showed you earlier that you can sort of lay these out. And so here I've done it differently. So now every column here is a vertex, as opposed to every row is a vertex, but you can take the transpose if you want. And I've just unfolded it. But here, what I've done is I'm considering a slightly different scenario where it's still 2 outcomes, binary outcomes, but what if Alice and Bob each have 3 settings? So then it's going to be way more than 16 probabilities. It's going to be like, I don't know, more probabilities to describe it, and potentially more columns, more deterministic strategies. But regardless of the number of settings, you can always figure out how many possible assignments there are. And so we get these vectors. And then we can do the same thing for the instrumental scenario if we wanted to discover what those look like. So here would be sort of these sort of probabilistic descriptions here, which is this is for x being 1 and this is for x being 2 in the instrumental scenario, and you have A and B. So here you have 1, 1, 1, 2, 2, 1, and 2, 2. And so you'll assign that every sort of block here normalizes, which has total probability 1. And these are the deterministic assignments to the instrumental scenario. Regardless of whether we're dealing with the instrumental scenario, the Bell scenario, or any scenario with a latent variable, we get these deterministic assignments. And then we can write it out as this matrix, which is just flatten it out because it doesn't really matter. And then to derive the Bell inequalities, we use software to convert from a vertex representation to a half-space representation. So here, for example, I'm doing this with, I guess, 3 settings. And this is an example of such a matrix. So every row is a deterministic strategy. And here we have 36 possible probabilities. And I've just made the first column equal to 1 because it's a constant term. The reason we do a 1 is because otherwise we end up with sort of super normalization and probabilities can be larger than 1. So I'm going to say that if it's extreme 1, we're going to put a 1 next to it. So 36, but it ends up being 37. And we just get these matrices, and I can just dump them into software. So there's some software called CDD, which is open source, fully available for doing convex Hull calculations. If I put that in, I discover inequalities. I get a matrix, but this matrix, I can then just understand it as inequalities, right? So here, for example, if I do it with the Bell polytope, I end up with things like this. And so I get, these are trivial inequalities, these are also trivial inequalities, and these are Bell inequalities. And you can see here, there's like this 1 plus, and that's because all I've done is just take this vector of symbolic probabilities, and the half-space representation is a description of inequalities. Just every row of the half-space matrix is the coefficients of the inequality. And if I do this for 3 settings per party, I might discover many more. Generally speaking, what you might find is that if you discover one Bell inequality, you usually discover many at a time. because who's to say that there's any difference between outcome 1 and outcome 2, right? I could relabel the outcomes, and it's certainly just as valid because it's just an abstract label. There's nothing special about yes as opposed to no as an outcome. They're just binary outcomes. Or I could exchange setting 1 for setting 3. And so there's this innate symmetry of the scenario, which means that one inequality implies many. So sometimes what we do is we're interested in discovering not all of the Bell inequalities, but all of the Bell inequalities up to symmetry. So you can get like a smaller representative set. And then there's software out there slightly different from CDD, which also does this convex hull stuff, but instead of returning all the inequalities, only returns the inequalities up to symmetry, and that's called SimPol. I'll send you the links for all of this software. And if I do that, then even though I'm discovering potentially hundreds of inequalities otherwise, I find that there's only 3 classes of Bell inequality when we go to 3 settings. And there are in fact websites which list many famous Bell inequalities if you want to sort of compare. And this business about inferring the strength of causal effects, which is the very last thing I'm going to say. So suppose that we have this instrumental scenario. And what we know is that here, if we have, you can think about Y as this auxiliary counterfactual variable. So it kind of looks like the Bell scenario. And if the original A coincides with the counterfactual, then it's observable data. And so if we do this to our counterfactual DAG, which there's a connection between the instrumental and the Bell scenario that I didn't elaborate on. So here in this notation, I'm calling the counterfactual instrumental scenario the Bell scenario, because that is a perfectly valid choice. Some of these are observed probabilities, some of them are not. So you can take your data and you say that your data does not completely specify these probabilities. You have unspecified probabilities, but that's okay, because you can then talk about a term that you want to evaluate, like what's the probability of getting B to equal the second outcome if you were to intervene and set A equal to 2. This is not something that you can measure, but it's something that you can express in terms of counterfactual probabilities. Because it's just in this counterfactual sense, it's the sum of the outcomes over the natural A. So you're kind of tracing that out. And so it ends up being the sum of these 2 terms. And so if we understand that, we can use our Bell inequalities or our Bell polytope. So here's an example of some actual instrumental data where we see confounding, and we say there's about a 70% chance that A is equal to X. There's about an 80% chance that B is equal to A. So this is data that I made up. And so you could say, if this is the data that I observe, what is the probability of getting B to equal 2 if I were to intervene and set A equal to 2, which is different from the probability of what's the probability of B equaling 2, given that I see that A was equal to 2, right? Counterfactual as opposed to factual probabilities. And if I do this, it's just a maximization problem. So I end up just saying, okay, given my the quantity that I want to evaluate, I can put in the numeric values which partially specify it. And then I have these other conditions, which are the conditions which are implied by membership in this polytope here, which I found from the convex hull algorithm. And it tells me that the smallest value for this unobservable probability is 0.4, and the largest value is 0.7. So this is the kind of calculation that we're doing, and I guess we can talk about class projects now. But not only can we use convex hull algorithms, which are used for discovering Bell inequalities, to do causal discovery and causal falsification, we can also use them to estimate the strength of causal effects and figure out what would happen if you changed things in causal diagram with a single unobserved variable. And that concludes the main things that I wanted to convey.
Thank you very much. Thank you, Elie. It was great that you actually went through kind of multiple different kind of sections of talks. Questions? Please feel free to just shout out your questions using audio, or if you prefer, write them in the chat window. Regarding the causal discovery algorithms that you mentioned, I was wondering, has there been any work done that connects discovery of quantum behavior at the macroscopic level, identifying whether it is actually genuinely quantum via testing, hey, there's a non-locality violation that's happening here, and then testing it against, hey, no, there's a better causal discovery, causal process that's a better explanation of those correlations. Does that make sense?
Maybe say one more time.
Right. So know how you've got these proposals like photosynthesis or avian migration, and people argue, hey, these processes in nature are using quantum processes, and then there's a debate about whether the underlying process is actually genuinely quantum. So one way, I guess, one could argue those processes are genuinely quantum is to argue whether or not there is a certain macroscopic non-local correlation under there. Now, would there be some work that says, hey, here's a macroscopic non-local correlation, but here's a causal explanation of those correlations in a macroscopic situation, which is a much better and reasonable kind of classical explanation of it, rather than a quantum non-local version?
So I think that's a great question. So let me say that this perspective of violating Bell inequality, right? So violating Bell inequality is to me the best possible way of showing that you've got something which is genuinely quantum. But I don't want to sort of minimize the other arguments for quantumness. There are other sort of demonstrations that people use, like spin squeezing, like contextuality proofs, computational speed up. For like factoring prime numbers, which have nothing to do with violating Bell inequality, but which are all sort of celebrated features of quantum theory. So when we talk about avian migration and whether that has quantum phenomena, as I understand it, I don't think anybody has appealed to causal structure as a way of justifying that. I don't think there's any suggestion that should be viewed as a quantum signature through this particular lens. It's more as though we're saying there's some tunneling, there's some energy barriers, there's some magnetosensitivity, which is resetting too fast to admit sort of classical explanations. So I'm not sure whether this is the appropriate lens. On the other hand, like if you could do it, if you could sort of do a analysis of some biological phenomena where you suspect that there's, that entanglement plays a role, and show that under the assumptions of causal structure, which are reasonable, that in fact you must have a quantum common cause somewhere as opposed to a hidden mirror model, that would be amazing. I'm sort of skeptical that that would be appropriate in a biological situation, but it's possible. Right. There's no work on that that I'm aware of today.
My concern was exactly this issue of when you take that macroscopic situation or experiment, whatever that would be. I exactly also don't know of anyone. How would one kind of go about identifying possible hidden causal influences in that macroscopic situation? And yeah, without kind of fixing one experiment, it's hard to kind of suggest how to go about it.
I don't know. It's really quite difficult. Again, we really have this nice feature that the scenario that Bell studied, the Bell scenario, is particularly amenable to trusting that if it was going to be classical, then there's really not that many possible classical causal structures that we can play with, because we can appeal to special relativity. We can say like, we can do these sort of loophole-free Bell experiments where it's just not plausible to entertain any possible classical causal structures other than these classical causal structures. And then the sort of the final nail in the hammer is that the remaining plausible classical causal structures fail. It strikes me that if you were doing a biological scenario where everything is sort of really close together, and you're dealing with sort of macroscopic phenomena, that you would sort of start with many plausible causal structures which are entirely classical, which could involve hidden variables models, but you wouldn't necessarily be saying like there's only one causal structure and it's either a hidden variable model or a quantum causal model. Right. And it's kind of like, if that's what you're deciding between, then great. Then you can say, okay, you do the signature from quantumness. But if you really have on the table quite a few plausible classical explanations, then even if you show that some of them would require quantumness, the other ones might not.